Hola Melina,
Hola, ¿qué tal? Un
qué gusto,
gusto.
¿cómo estás?
Muy bien, ¿vos?
Bien, gracias a Dios.
Me alegro.
Yo tenía que darte paso a la interpretación, ¿verdad? Añadir
Sí,
intérprete, ok. Yo creo que ya. Hi Mary, how are you?
I'm great. I'm sorry I came an hour early. I was misreading my calendar.
Ah,
It said 11:50 and I'm thinking 11, not the 50.
okay. I'm setting the interpreter. We have a simultaneous interpreter for the people who don't speak English.
Okay.
Melina, entonces, intérprete de español a inglés, ¿verdad?
sí. De inglés a español, pero no importa, es lo mismo. Poné cualquiera que te.
Ok, voy a poner inglés ya que está ahí a español.
Sí, ahí está. Y
¿Cómo? ¿Qué me decías?
Hello. Do you want me to say
Hola.
something?
Yes, I think that her partner is waiting in the room.
Ah, okay.
Ya admití a Patricia.
There we go.
Hola Patricia.
Can't hear her because she's in the interpreter channel.
Do you have some special requests, Mary?
No, I don't have any computer audio, but I would like to test that I can project.
Okay, go ahead. Do you have the permits?
I think so. Let me try. Host disabled. No, I don't have permission.
Let me, okay. I think you have it now. Please try.
Okay, you can see that, yes?
Yes.
You see the, that's the wrong share. Never mind, I want to unshare. Well, you see the presenter's mode, yes?
Yes.
That's wrong. I need to unshare. How do I do that? Oh, over here. No,
Yes.
no, you just see the first screen.
The blacksmith kitchen.
Right, but you don't see the next slide.
No.
Okay, so you've got the right share.
Okay.
Yeah, okay, it's great. Shall I leave it shared? I could do one.
Yes, yes, you can. You can
Okay.
leave it like that.
And now-
I'm going to admit the
Wait a minute,
persons.
wait. Okay. I have to see if this works. Yes, okay, there we go. So I'm going to explain the blacksmith's kitchen because it was going to be the shoemaker's children, but I found out I should talk about the blacksmith's knives.
Okay.
Hola, buenas tardes.
Hola.
Hello, good afternoon.
Hola Patricia.
Hola, ¿cómo estás? Yo soy Patricia, soy la otra intérprete junto con Melina.
Ok. Cuando estaba Melina, yo pude ponerla a ella de intérprete, pero ahorita no sé cómo ponerte de intérprete a ti.
Tenés que hacer de la misma forma, que me
pero
podés
es que
ingresar
no me
manualmente
sale.
como intérprete.
No me sale, espérate, no me sale la opción esa.
What does that black thing say there, top?
16 people.
No me sale.
Okay, all right,
We're screen sharing.
fine.
Those are the red dashes, stop share.
I understand that. I just didn't know what the black one was. It says how many people are in the waiting room. So will I be introduced?
Yes, I will introduce you.
Okay,
Could you please admit the persons in the waiting room until I put Patricia in like interpreter?
me?
Could you do
I
that?
do not know how to admit people.
No, I don't see Patricia, ¿tú ves a las personas que están allí para admitir?
Yo veo que hay 4 participantes.
¿Tú puedes allí admitirlo, por favor? Es que no los veo acá en mi pantalla, por eso es que...
No, pero es que yo veo solamente 4 participantes, pero no sé quiénes son las personas en la sala de espera.
Ah, nosotros que
No,
estamos acá.
claro, yo puedo ver, claro, las 4 personas que estamos acá en la sala.
So can I,
Lo que entiendo es que me parece que para poder hacerlo tenés que ser el host.
Pero yo soy el host.
Ah, entonces creo que deberías poder
so
ponerme
I
como
have to admit
intérprete.
them? What does it say, Tom? I can't see that.
Al menos que... ya sé qué fue lo que pasó.
Close it.
El host ahora es Mary, porque yo la
Claro.
puse de host.
So should I
Claro.
stop sharing so you can admit people and then start sharing again and nobody can come after we start sharing? I do not know how to admit people.
I can do it, pero ahora no me, ay, a la vida, es que como puse a Mary de host, ahora no me
Claro.
sale la opción. Patricia, ¿tú sabes cómo sacar de nuevamente la opción esa del host? Pedir que, ya aquí está, reclamar anfitrión.
Ahí
So I
está.
stop sharing?
Ya, ahí estás vos como
it's okay.
hospedadora.
Ajá, ahora
Ahí estás vos
yo creo que te puedo poner a ti de la cuestión del intérprete.
Sí, en Language Interpretation creo que
Sí,
tenés que ir.
dame, acá está. Ok, voy a admitir a las personas. I'm going to admit the persons that are in the waiting room, Mary.
Yes.
Listo. Hola a todos y bienvenidos. Vamos a esperar que vengan un poquito más de personas, que sean las 12, son las 11:59, para entonces presentar a nuestros speakers de hoy. Bienvenidos todos.
Gracias.
Gracias, buenos días.
Buenos días.
Para todos, esta sesión va a tener interpretación simultánea, así que ustedes pueden allí en el Zoom seleccionar el canal que ustedes quieran, si quieren escuchar la exposición en inglés, de boca de los speakers, o pueden entonces también escucharla a través de nuestras intérpretes que son Patricia y Melina. Bueno, siendo las 12:02 y ya habiendo emitido, ahora que después que presento a nuestros speakers, entonces vamos a admitir a las otras personas. Okay. Vamos a hacer la última admisión de 3 personas más. Ahorita tenemos 38 participantes en esta sesión. We are now 38 participants in this session. Vamos a hacer la presentación de Mary y de Tom para esta sesión tan emocionante de las 12 del día, de nuestro primer día de las jornadas latinoamericanas de agilidad. Buenas tardes, gracias a todos por estar aquí. Nos alegra darles la bienvenida a esta sesión. Ustedes son lo más preciado para esta comunidad y quienes formamos parte de la organización nos comprometemos a fomentar un ambiente acogedor, seguro e inclusivo antes, durante y después de estas jornadas. Las sesiones de este evento serán grabadas y estarán disponibles para quienes participen en este encuentro. El sistema dará aviso en cuanto se inicie la grabación y en caso que no desees aparecer en la grabación, solamente apaga la cámara. Nuestros speakers de esta sesión son Mary y Tom Poppendick. Ellos llevaron los conceptos Lean al mundo ágil a través de sus 4 libros sobre desarrollo de software Lean. Están casados desde hace más de 50 años y han trabajado en equipo durante las últimas 2 décadas para mejorar la profesión de la ingeniería de software a través de talleres y charlas, podcasts y entrevistas. Por favor, démosles la bienvenida a Mary y Tom Poppendick. The mic is all yours, Mary.
Okay, thank you. Good morning, or maybe it's afternoon. It's sort of right in the middle of the day today. I was going to talk about the shoemaker's children, but then I found out that in Spanish, you don't talk about the shoemaker's children, you talk about the blacksmith's kitchen and the wooden knives. So I changed, and we're going to talk about the blacksmith's kitchen has wooden knives, but in English, we always say the shoemaker's son always goes barefoot. So it's basically the same concept. If you go back 20 years, and it's 2001, Google is struggling to search through 1.3 billion web pages. That's not very many when it comes right down to it, but that's how many they search in 2001. They've been around for a while. They've just gotten out of beta. And it's not nearly the ubiquitous thing that it is today. At the same time, Amazon is struggling with a monolithic architecture. It has a big front end, a big back end, and it just can't keep up with what's going on in their, especially their holiday season. There's a really interesting talk in 2015 on AWS reInvent by Rob Brigham, and I will talk more about that later in this talk. But this is a picture that he had of a big monolith by Lake Washington. Mobile phones looked like this in 2001. And if you see, there's no screen, there's a keypad on the device and so on. And there's no cloud. So that's what it was like in the world of technology 20 years ago. And that's when we who were doing software were solving other people's problems, but not our problems. So IT software was used at that time to automate business processes, and engineering software, the kind I'm most familiar with, was used to automate equipment. And that's what software engineers did, was they either automated business processes or equipment. But we did not automate our processes. They were largely manual and they were very slow. We had manual acceptance testing, manual source code control, manual release management, manual hardware provisioning, manual production monitoring. We were using wooden tools. And even though we were the people who made the tools for other people. So what happened? And what Agile actually is all about is we learned to make better tools. We used software to start, so we started to use software to solve our own problems. And the first thing we did, really right at the beginning, was we invented or got going on free and open source software. So back in 1985, Richard Stallman did the new manifesto. And basically it was software ought to be free. And everybody thought he was pretty crazy. But in 1991, not that 6 years later, this Helsinki student wrote an operating system just for fun. And in 1993, not that much later, a group of 8 developers started enhancing the NASA National Center for Supercomputing server in Urbana-Champaign, Illinois. 10 years, 9 years, 8 years later, IBM invested $1 billion in Linux. And not that much later than that, in 1999, the Apache Foundation, the Apache Software Foundation was founded by that group of 8 developers that started. Today, Apache is used by over 40% of all websites. We do a lot with our tools by figuring out, first and foremost, that we can make whatever tools we want, and we don't have to worry about commercializing them if we put them in the free and open source area. And massive amounts of software development tools can be found in free and open source software. We share our tools and we improve them. And here's just a few of the various things that happen to help us do things better. You'll recognize a lot of these, and I'll be talking about most of them as I go through here. The next thing we figured out how to do was horizontal scaling. So this, you might not realize it, but this is an absolutely landmark paper in 1988. It created a massive stir in Silicon Valley because it was called a case for redundant arrays of inexpensive disks. And it was published in a conference in 1988 and raised a lot of eyebrows because its basic message was lots of stuff that fails a lot can be more reliable than one big thing that rarely fails. How can this be? The trick is if you replicate things and use fault detection to remove and recover the bad pieces and keep the software running, you can take a whole lot of inexpensive things and make them more reliable than a great big thing that almost never dies. This was a novel concept in 1988. Really, a lot of people didn't know what to do with it. But actually, when it comes right down to it, Google did. If you go to about 2000, so that's maybe 12 years later, Google's indexing software just wouldn't work anymore. Nobody could figure out why. But these 2 software engineers, Jeff Dean and Sanjay Gemwat, put their minds to work on looking at every last detail of what was going wrong with their indexing software. And they discovered that faulty hardware, faulty memory was causing the indexing software to fail. Now, memory failed very rarely, but it occasionally failed. And they put so much pressure on memory that they got to that occasional failure way too often. And so what did they do? They went to the array of inexpensive parts, and basically they invented the Google file system where they took the whole set of data that they had and put it into little chunks and replicated it 3 times, had some chunk servers and master to keep track of where stuff was. And they spread the data in 3 different versions, 3 different copies across whole bunches of cheap, inexpensive hardware. That's the way that the Google system, even today, is highly reliable, because lots of little things can be a lot more reliable than a big thing, because you can replicate it, find the bad stuff, and get rid of it, and still have a couple of backups. They published a landmark paper in 2003 talking about this, and it was really an eye-opener. At the same time, they had been using the same process on their hardware, and in 2003 they also published, Google, and Jeffrey Dean was involved in this one too, Web Search for a Planet, the Google Cluster Architecture. And guess what? It was a whole bunch of inexpensive computers. Now, when this paper was published, I can remember reading it and saying, oh, wow, that is really something. So that's how they do it. Today, lots of inexpensive hardware that's replicated is common, but then it was absolutely revolutionary. So their architecture had clusters of more than 15,000 commodity class PCs with the fault tolerant software a huge amount of fault tolerant software that allowed them to throw out the bad stuff and keep everything running smoothly. They found they had increased reliability, much reduced latency, and a lot lower cost. Who would have thought? So when it came to data, okay, we also had horizontal scaling. And in 2001, the Apache Foundation accepted Doug Cutting and Mike Carafella's Lucerne search software. And then they decided, since they had search software, they should have a web crawler. So they got one called Nutch, and they were having a huge amount of trouble making their web crawler work across multiple software, across multiple hardware, because it's very complicated to figure out how to do that. But then in 2003, remember that file system paper was published, and they took a look at it and they said, oh my goodness, that's got to be it. And they just kind of said, okay, this is our spec. We're going to make our web crawler work like this. So they came up with something called a software managed file system called Hadoop file system. And then a year later, the MapReduce paper came out from Google, and it talked about how do you search all of this stuff in this file system. And they copied that, and it became Hadoop MapReduce. And then in 2006, Apache Hadoop was released, and Doug Cutting joined Yahoo. And what happened the next 6 years across Silicon Valley is all different kinds of companies started using this open source software at Apache that could do the same kind of file system that Google had published its first paper on in 2003. And this file system with multiple copies of things spread across multiple small disks became the way that really reliable software was done. By 2012, Hadoop had gone mainstream with public companies like Cloudera and Hortonworks and Spark, trying to get money by helping people use open source software. But in that same year, 2012, there was another breakthrough in the data area. And that was the ImageNet Challenge created a breakthrough in artificial intelligence. Suddenly, people figured out how to do massive searches of data and train machines to recognize patterns. This breakthrough in 2012, probably the biggest to date breakthrough in artificial intelligence, although I'm positive there are a lot more that have to be on the table, because it's not really intelligence, it's artificial pattern recognition. The next big thing then in 2015 was not the Hadoop stuff, but it became the Tensorflow, which also was open source by Google. So another kind of horizontal scaling happened in the same time frame, and that was transaction processing. So you have in 2000 in the holiday season, remember Amazon's big monolith? Well, they could not keep up with their orders, and they had to do something. They had to either figure out how to handle a whole lot more transactions, or they had to figure out how to break the transactions apart into small pieces and handle the small pieces. And it was heresy to say that you could break apart a transaction, because databases handled transactions. And if you broke them apart, you had to handle all of the pieces of that transaction yourself with software. So it was a massive undertaking to do it, but they chose to do option 2, which says break the transactions into services. So they broke the transactions into services, but having all these services, if you remember Conway's law says, your organizational structure and your software structure are going to match. The architectures will be approximately the same. And what happened at Amazon is they formed a lot of, we'll call them 2 pizza teams of 8 to 10 people that could be fed lunch with 2 pizzas. And they were each responsible for a service. And most importantly, the theory was you can't constrain these teams. You have to let them act independently of other teams, because if they are tightly coupled, then you basically get back to the box around the transactions. So they found out if the teams could be independent and work separately on individual services, things went faster, they were lower cost, and they were way more reliable. So if you think about Conway's law, which basically says your architecture and your organization will match your architecture in your software, that is what brought us the cloud. So as you take these two pieces of teams at Amazon, and they were autonomous, and because they had autonomous service teams, that meant the teams could deploy independent of each other. So what happened? Operations went nuts. They went crazy because all of a sudden, all the failures that happened with the release were happening all the time. Chris Pinkham was the vice president of infrastructure, and he said, all right, since I can't change my boss, Jeff Bezos, dictate that these teams are going to be independent, I think we have to have self-service deployment so those development teams can be responsible for their own problems. And maybe if we could figure out how to do this, we could sell it. So he made this proposal, but it didn't get a lot of attention at first. So he went back to South Africa where he had grown up because he wanted to raise a family. And then after a while, you know, the executives saw Pinkham's proposal and they said, sounds like a good idea. So they called up Pinkham and said, hey, would you pursue your idea there in South Africa? Hire a team in South Africa and put together some way that teams can self-deploy. And in 2 years, that team developed EC2, which is the first Elastic Cloud release from Amazon. It launched in 2006, and the rest is history. Because today, that is the basis of Amazon Web Services, which is, well, at last time I looked, it was $45 billion a year and growing fast. So if you think about it, internet scale economics changes the rules. The horizontal scaling concept is the only thing that can accommodate something that is as big as the internet. So if you look at an enterprise installation, and this is from a talk by James Hamilton in 2008, but it's, you know, it basically shows why the cloud grew. At that time, enterprise installations were about 1,000 servers. The main cost was people, roughly one admin to 100 servers, okay? And the number of people grew linearly with the number of servers. So if you had 200 servers, you had 2 admins, and if you had 1,000 servers, you had 10 admins, and so on. So if you're going to scale up, you want to get fewer, bigger systems, so you would have fewer admins because that was your major cost. Now let's go to internet scale installations, the kinds of things that Google and Amazon put together in that same time frame. They had clusters of 1,000 servers, clusters of data centers, of servers that were the size, each one of their clusters was the size of a whole enterprise data center. So they were massive. And because they did that, they had to find software to manage those clusters. And because they were able to do all the management of the clusters, not with admins, not with people, but with software, the costs at the time were 6 to 7 times lower than enterprise installations per any server or per any amount of software or service that was provided. So in the internet scale installations, the main cost is hardware and power. People are just 5 to 10% of the cost. So therefore, what you want to do is use more smaller commodity components and do horizontal scaling. So if you look at it, the economics of the cloud, because it is so much cheaper to provide compute power, that's what drove its widespread adoption. The fact that we use software rather than people to manage the servers. And then comes 1999, and this book is published, Extreme Programming. And in that book, one of the novel, really radical concepts was test-first development. As to quote the book, Kent Beck said, any program feature without an automated sys doesn't exist, it's not allowed. Programmers write unit tests so that their confidence in the operation of the program can be part of the program itself. So if you write some code, you also have to write a unit test. Customer, and it's run as part of the program. Customers, that's somebody who's going to use the system when it's in production. They're the ones who write functional tests, and then they're also part of the program because that allows them to have confidence in the operation of the program. Radical, certainly there. JUnit was the first testing framework published by Kent Beck in 2000, and lots of unit testing frameworks came shortly thereafter. At the same time, he proposed this concept of continuous integration. Code is integrated and tested after a few hours, a day at most. Integrating one set of changes at a time works well because it's obvious we should fix a test if it fails. If we can't get the test to run at 100%, throw out what we just did so that the tests are always left running at 100%. So the concept is you're constantly integrating code, little bits of code, and you throw stuff out if it doesn't pass the test. And there's always tests to test everything. So Cruise Control was one of the first open source software projects that supported this continuous integration. It came originally from ThoughtWorks, and it was really a radical concept in 2001. But all of this stuff, test first development and continuous integration, is really easy to talk about, but it's awfully hard to actually do it. It took us years to figure out how to actually make that work. We also had this concept in extreme programming of refactoring. And that is after they have added the features, the program asks if they can now see how to make the program simpler while still running all of the tests. So you constantly simplify the program. You take the time to simplify the program. Again, easy to say, but easy to ignore. However, it turns out refactoring and cleaning up the code and making it simple is essential. And one of the nice open source tools that helped us do that was Eclipse. At the time, it was a IDE, integrated development environment, that helped a lot with the refactoring. But if you look at these, what some people call engineering practices, they're not simple. It took, I don't know, a decade to figure out how to really do effective acceptance tests. It took a long time for people to catch on to the fact that you can't test everything unless you have very well factored code. That is code broken up into small enough pieces that you don't test everything. You simply limit the interactions of things and test a piece plus its interactions. That's the way it ended up working, but it took a long time to figure that out. Then comes infrastructure as code. So if you think about this concept of friction, I will call it large system disease. So I want to show you what friction looks like. Here's the 1950s. And these are people loading a ship. Okay. They're what we call longshoremen here in the US. There are other names in other countries, but they loaded ships. And you can see they loaded individual pallets of stuff. You know, stuff fell down. If they didn't load it right, the ship could shift during a storm and sink. So they had to be really careful about it. The ports around the world had jobs for hundreds and thousands of folks that would go in there and pack up the ships and unpack the ships. But that was a very high friction environment. And you have to see friction before you can reduce friction. And nobody really recognized the friction here until this here guy in 56, Malcolm McLean, who was a owner of a truck, and he needed to move his trucks up to from the southern part of the US up to New York or New England. And he said, well, why can't I just drive my trucks on a ship? Why do I have to have them unpacked and then repacked? Well, because the longshoremen had a monopoly on loading ships and they didn't allow trucks on. Well, he didn't think that was such a good idea. So there is this book called The Box, and it talks about how shipping containers were invented, starting with McLean, to reduce friction in the shipping environment and changed basically how we ship stuff around the world and had massive economic impact. Because by the 1970s, by 20 years later, This is how almost all goods were shipped. And even today, that's the way goods are shipped. It's much lower friction than the high friction of the 1950s. Now, the same concept applies to software. If you look at the hardware in, I don't know, the mid 1990s or 1980s anyway, that's what it looked like. I mean, I worked with hardware that looked like that. But then comes virtualized servers, especially in the 2000 to 2010 time frame. And you can see companies like Yahoo and Google figuring out how to do this. And the virtualized servers are what was necessary in order to support those automated data centers. So that's what a virtualized server looked like. And there was less friction, it's true. But, you know, starting in about 2011, we had another layer of simplicity, and that is containers. So Docker came along and it put another layer on there, and it allowed whole bunches of not just 3 apps, but multiple apps to work on a single server. And that's even lower friction. So now, if you look at what's going on even today, starting in 2015, we kept reducing friction. In 2015, the concept of serverless functions, what Google calls Lambda functions, was introduced, and it's become quite popular for certain things. But these are self-provisioning, event-driven, very short functions. They run in the cloud, and they're faster and simpler and lower cost than having the developers think about provisioning hardware, even if they're provisioning it in software. Very low friction. Doesn't solve all problems, isn't great for everything, but when it works, it's a very nice low friction approach to software. And then we added some more things. We added edge computing and Internet of Things, gave us increased reliability, reduced latency, lower cost. And now we moved into software-defined networks. So even the network hardware went away, and we did all of that in software. So the concept of infrastructure as code has continued to be developed and continued to allow us to do all sorts of stuff that used to be done in hardware in software. Now let's go to 2010, when the book Continuous Delivery was published. Its target audience was enterprises, and it told enterprises they could go ahead and deliver software into production all the time. It was a radical idea. And the interesting thing about this book is that it talked in detail about technically how a company would go about doing it. It used acceptance test development process, acceptance test driven development process. It required cross-functional teams that included product people, test people, QA people, operations people, everybody. And you automated both the build, the test, database migration, deployment, the whole thing. Everything was automated, and you did incremental development on the trunk. You did trunk-based development and continually integrated into that trunk. Software was always production ready, or everything stopped until it is, because that's the highest priority. And in some cases, software is always deployed to production as soon as it's ready. And you keep deploying things to production, even if you're not completely done with a fairly complex change, because you put stuff on switches and you constantly deploy software in its current state, but you keep stuff off until you are ready to switch it on. So your features are released by switch, not by deployment. So the moral here is, if it's hard, build software to do it for you. That's what we learned. Our hardest problems are much easier to solve if we solve them through software than if we keep batting our heads against a manual wall. So people built continuous integration, continuous delivery pipelines. And one of the interesting tools that was open source is Kubernetes. It's a toolbox to allow you to do continuous integration and continuous delivery. And then the next thing was, we have to think about low dependency architecture, because testing, continuous delivery, all of this stuff is really hard when things are tightly coupled. The dependency between pieces of the software has got to go. We have to have very low dependency hardware. Now, if you think about it, we used to think that databases were the most important thing in an enterprise. And in fact, an enterprise architecture looked like this, with business, data, applications, technology. And the data had to be a single system of record, not duplicated, all in one place, all on a single server. But the problem is, if all of the apps used one single database, that database couldn't have any changes to it without every single app that depended upon it being retested. And so what you did was, with a single database, you tied all the apps together in a dependency deadlock. And if you think about it, those big central databases were massive dependency generators. That's why we don't want them anymore. Instead, we went to a federated architecture. If you think of a federated architecture, think of a smartphone architecture, where you have individual apps that don't talk to each other, that have their own data, and that might integrate through the cloud or something like that. Microservices architecture is basically the same concept. There's a technology platform or a service mesh. There's some data, there's some business logic, there's some applications, but they're not tightly coupled. They are separately deployable and integrated. And typically they are built on top of the cloud. The data stores there are distributed. And that's what Amazon developed when it figured out how to solve its deadlock problem. But when I first heard that Amazon wasn't using central databases anymore, I was astonished. I couldn't believe it. Everybody that did transaction processing had to have a central database, didn't they? Turns out, bad idea. So it took us a while to figure that out. But when you have this kind of architecture, a lot of the things that we want to do with continuous delivery and many of those other things suddenly become available, because you can have small independent teams operating independently and therefore much faster. So that's an enabler for business agility. So if we put this all together, let's go back to Rob Ingham's talk at AWS reInvent in 2015 that I mentioned earlier. So he talked in this talk about DevOps at Amazon. And the first thing he did was say, well, what is DevOps? And if you look at the software development life cycle, you want to build, test, release, and then based on the results, you want to monitor them, and then you want to plan the next one, and you have a loop. And DevOps, he decided, was any efficiency that speeds up this life cycle. Now, if you think about that, DevOps as efficiency speeding up this whole life cycle, not just the delivery, but the plan, the feedback loop too, and making the whole cycle go faster. That's how he defined DevOps. Then he believes that the speed of completing this loop is what determines your business agility. And there's a whole lot to be said for that. So back in 2001, that cycle at Amazon was, as he said, embarrassingly slow. There was a big app and there was a big delivery pipeline with all sorts of people in every set, lots of engineers worrying about the build and the test and the release. And there was sort of the big app. So the developers were all feeding into a single pipeline. And not just the build, test, release, but then monitor and plan the whole thing. Very high friction because hundreds of developers had to interact with each other in order to get anything done. Extraordinarily slow. So that's a monolith development cycle that they had in 2001 in Amazon. And they eventually, by 2014, were at this kind of thing. Lots of services, a few developers for each service. And each service has its own build, test, release, and monitor plan cycle. So every single one is independent of the other one. And because the delivery pipelines are independent, they go much faster and you don't have to wait on any of the other ones. So much lower friction. And by 2014, which was just before his talk, they were doing 50 million deployments a year at Amazon. And that was 2014. You can imagine what they're doing now. So business agility comes from very rapid loop ability to go through this loop. And that comes typically from a architecture that gives independent teams the ability to operate separately and operate quickly. Now, when you go to AWS and you don't go to their very rapid growth, there is a book and it's called Working Backwards. And the advertisement for it says, how did Amazon do it? How did they get to the place where they figured this stuff out? Because really, they figured it out kind of before the rest of us. And they didn't figure it out using a process that somebody else had developed. They figured it out inventing their own process and not specifically copying anybody else. Because if they copied somebody else, then they would have somebody else's solution to their problem. So this is a really interesting book and I recommend it. And one of the most important things in this book is the chapter called Beyond Two Pizza Teams, Single-Threaded Leaders. They discovered that two pizza teams were not the whole answer. And there was something more important to make sure that they were able to move effectively and quickly. And it's what they now call single-threaded leaders. Because they discovered through lots of experiments and data that the biggest predictor of a team's success is a leader with the appropriate skills, authority, and experience to staff and manage a team whose sole focus is to get the job done, whatever job that team is focusing on. So people are not doing multiple things, they're so focused solely on one thing. The leader sole focus is to get this team together and make it happen. And the single-threaded leaders have nothing else to do but to assemble this team and get the job done. The team is also focused only on one thing, and that is to get this job done. And when they did that is when they got the best results, the most successful results. Because as Dave Limp said, the best way to fail at inventing something is by making it somebody's part-time job. So the concept of focus, both on the team and especially on the part of the leader, is one of their most important predictors of how do you do this rapid, constant invention of new things. So let's talk about, in summary, technologies that enable business agility. I'm going to talk about the old way and the future. The old way, we did proprietary software. Now we do open source. The old way, we did vertical scaling. We've got bigger and bigger computers. Today, we scale out. We do lots and lots of small stuff and manage it with software. We used to have hardware provisioning. Instead, today, we have on-demand infrastructure. When I run into a company that has a bottleneck, which is hardware provisioning, anymore today, I can't believe it. How can you still be provisioning hardware manually when you could be doing it with on-demand infrastructure? But I still run into a few of them. Testing at the end is not the way that happens. Testing is the specification of how the thing should work. So tests are written first, not last. Periodic releases are interesting. And they used to be very periodic, 6 months, years. I know a lot of software that had 2 and 3 year release cycles. Wow, imagine that. In 1999, I read an article saying, there are companies out there, you weren't going to believe this, but they actually release software every 3 months, or anyway, every 6 months. Isn't that remarkable? Well, right now, every 3 months or every 6 months is remarkably slow. Continuous delivery is the way that most companies have figured out how to go. Instead of a monolithic architecture, because if you have a monolithic architecture, you really have to have periodic releases and link everything and test it together. But a federated architecture gets you beyond that. The database is the integrator in the 1990s world of enterprises. Today, APIs are the integrators. And the product owner is the old way, not responsible for any of the above stuff, just responsible to tell the team what to do and let it figure it out. A single threaded leader is responsible for all of the above stuff. Single threaded leader is not a coach, is not a product owner, is a person completely and wholly dedicated to assembling a team and getting the team completely dedicated to getting the job done. And that's how we get very agile organizations. So with that, I have finished my talk, and I think I've got all of 2 minutes left in the 45 minutes. If you want to do some questions, we could probably do 1 or 2, but we could also say, thank you. What is the thing that you'd like to do?
Thank you, Mary, for this session. That's a very rich session. Too much information that you gave us today. Very useful, very useful. Sí, para los participantes de la sesión, por favor, si tienen alguna pregunta, pueden hacerla, abrir sus micrófonos y hacerla. Recuerde que tenemos interpretación simultánea para poder hacerla en que Mary también pueda entenderla si la hacen en español. Mary, do you have an icon at the bottom of your screen that says interpretation? You can switch there so you can hear the interpreter when a person in the audience.
I'm going to have to stop sharing to see that, I think.
Yes, yes.
Okay. All right. Tom? Okay, then what do I do?
You have an icon at the end of the bottom of your screen that says interpretation.
I don't see interpretation.
You don't
Here
see
we go.
it.
I see it. Okay. Click on that.
Okay. Yes, and you have to choose one channel.
English.
Yes.
Okay. Got it. Closer.
¿Alguna persona tiene alguna pregunta para Mary?
There are some questions in the chat.
Okay, let me see. Mary, did you hear it? Do you hear my voice or do
I hear your voice, but you will have
Okay.
to read me the questions because
Yes, I'm going to read it to you. Could you explain more about single threads leader?
Yes. I'm going to introduce my husband, Tom, who's joining us for the Q&A session for however long.
Hi, Tom.
Hello.
I really recommend the book Working Backwards. Two pizza teams worked well for Amazon in development, but as they tried to expand it to the other parts of the company, they didn't work so well because they weren't tailored to the ability to have very small teams, and you can't always have completely independent, very small teams. There are, if you're trying to put a satellite in space, things are interrelated. But they found that you could have a particular job that was the size of a small team, and you could have a leader that you assign to make that thing happen. And then that leader could maybe break it up into other small pieces and assign a leader to make some pieces happen. So if you have a single threaded leader, they basically are responsible for taking a particular problem that they're handed, that they have the skills to assemble a team and solve, and it's their job. It's their only job. And the team that they assemble, it's their only job. And when you can divide problems into pieces and assign them to a single person who has nothing else to do but solve that problem, and they have the authority to put together a team and have that team work with them to solve the problem, that's the way that Amazon moves so fast. That's the way that AWS is able to put, I don't know, how many enterprise scale pieces of software does AWS put on the market every year? a dozen or two, and they've been doing it since 2012. I don't know any other company that can field so much enterprise quality software so fast. And they do it with this concept of single threaded leader, where a issue, a problem is assigned to a competent person who then has the authority to put a team together and have that team solve the problem. Now, this is not the concept that the leader doesn't have responsibility. In fact, it's exactly the opposite. The leader is responsible for assembling the team and solving the problem. And they are responsible to make sure that the team that they assemble is both competent and is focused on only that problem. And when people focus on one thing and have nothing else to do but focus on that one thing, what we have found in the whole lean environment is that's when stuff gets done. And it gets done right, and it gets done quickly.
Every decision has a cost. And when you have one responsibility, all of your capabilities of making good decisions can be focused on achieving that goal. When you have multiple responsibilities, a significant part of your capability of making decisions is going to be soaked up in deciding which responsibility should I pay attention to next. So it destroys your ability to get things done because most of what you're doing is deciding what to pay attention to next.
Okay, thank you. We have another question. We have like 2 minutes to close this session, and I'm going to read the question. How do you handle detractors? I see that this is the only way to real agility, but I've been facing technical people saying that this path is not possible, nor realistic.
I'm not sure what it is that's not possible or not realistic, so I'm not quite understanding the question.
Fabián, ¿podrías hacer una ampliación?
Hi, thanks for the talk. I've been trying to coach the teams, to mentor the teams, trying to get to a real continuous delivery and release on demand. And it's really exhausting because every time I face the same issue with them. This is not realistic. We cannot do, for instance, TDD or whatever, because we need to focus on deliver.
So my guess is the problem is architecture. Generally speaking, if you have a tightly coupled architecture, in fact, continuous delivery is not practical. So if that's true, then you have to acknowledge that with your current architecture, you can't do it. But it's worth it to address the architecture. And that's really asking an awful lot of an organization that doesn't understand how serious monolithic architecture can get in their way of delivering stuff. So the other question is, who's making technical decisions? Non-technical people or technical people? If you have people in charge that are really working on focusing on achieving financial objectives and don't understand the underlying technology, then they're not going to buy into the concept of all of the pain and effort and long-standing work of changing the architecture. If you look at Amazon, it took them with their monolithic architecture from 2001 to approximately 2005 or 2006, like 5 years to move to an architecture with supported services. And in that time, they had a CEO who actually had studied software engineering in college, who understood their problems and who hid them and protected them from the focus on financial metrics and getting features delivered so that they could change the architecture so that his long-term vision could be accomplished. Now, if you don't have a leader that understands the long-term technical benefits of changing the architecture, your detractors are right. It's not possible. It's not going to be done. So you need to look at where are the decisions coming from And do they have any chance of understanding the impact of their blocking the concept?
Thank you,
Context-
Mary, for your answer. We are done in this session. The other speaker is waiting. Thank you very
Okay.
much. Gracias a todas las personas que nos acompañaron en esta sesión. Ya está el otro speaker esperando para entrar a la sesión. Muchísimas gracias y esperamos verlos en todo.